Welcome back, fellow chemists. We're on part 2 of the notes for Unit 4. We are on what the electrons are doing, and we're going to do a few different models. We're going to start with Bohr model, and we're going to get a little bit more complex, but a little bit more correct too. So this one's called the Bohr model. This is what they usually represent atoms as, and it looks really cool, looks nice, looks symmetrical. It is kind of correct, and it's really helpful to understand this and help us to know why the periodic table is arranged the way it is. So we're going to study it even though it's not 100% correct. So in Bohr's model, he said the electrons move around like planets around the sun. So if you go back to that picture, it looks like planets going around the sun, and the nucleus would be the sun, and a lot of things that make sense about it. Now, the farther away the electrons move from the nucleus, the more energy they have. And there is no in-between energy levels. So they're either at one level or at another level. Now when you draw the Bohr model, there are certain numbers of electrons that you can have at each level. You can only have 2 at the first level, you can only have 8 at the next, and then 18, and then 32, so it goes on and on. I'm going to go to this model right here. This one starts off good. We have the nucleus with the protons and the neutrons, and the first ring does have 2 electrons. Now the next ring should have some more. We have 1, 2, 3, 4. We need to put some more. 5, 6, 7, 8. So that would be more proper. We'd have 2 on the first ring, 8 on the next ring, so that's 10 electrons, and then 11, 12, 13, 14, 15. This one has 15 electrons, so that would be a perfectly fine model for phosphorus. Okay, so that's how you draw the element phosphorus. It's electrons, and we know that it has on the outside ring 1, 2, 3, 4, 5 electrons in the outside ring. So I'm going to draw another one just so you get the idea of how they should look. I will draw one for lithium. And lithium's numbers in the periodic table are 7 and 3. So we would put 3 protons in the middle, 4 neutrons in the middle. That's our nucleus. And then our first ring would hold 2 electrons. And the next ring would hold our third electron. We have a total of 3 electrons, and the Bohr model for lithium is done. Now I'm going to do another one on that very first row. We'll go to, let's do fluorine. Fluorine's numbers are 19 and 9. So I'm going to put 9 protons and 10 neutrons. Remember, we subtract to get neutrons. On the first ring, we're going to have 2 electrons. On the second ring, we're going to have 1, 2, 3, 4, 5, 6, 7. Okay. So it gives us a total of 9 electrons. Why didn't we go up to 8? The first level holds 8. Well, it's because we were done. We only needed 9 electrons. We had 2 on the first ring, 7 on the next ring, and that equals our total of 9. Now let's go to another screen, and we're going to try probably the biggest one we would be doing in the test. We'll do chlorine. Its numbers are 35 and 17 on the periodic table. So we put 17 protons, subtract to get 18 neutrons. And the first ring, orbit, whatever you want to call it, has 2 electrons. Next one's going to be full with 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to put 7 on the next one. 1, 2, 3, 4, 5, 6, 7. And really it doesn't matter if you have them spaced out evenly or if you have them all bunched together. Remember, the Bohr model isn't exactly perfectly correct, and it might just be easier for you to count them all. But that would be the complete Bohr model for chlorine. Now the Lewis dot structure is next. The nice thing that's easy about the Lewis dot is all we do is we take that element and we put the number of valence electrons. Valence means extra. Chlorine has 7 extra electrons. So we do 1, 2, 3, 4, 5, 6, 7. Okay. So that would be our model for chlorine. 7 valence electrons. And going back to lithium, we could do those. Lithium would have just 1 dot. It has 1 valence electron. And fluorine, we spaced those out earlier. We have all these, still 7. Fluorine would have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Okay. You might also notice that there's a connection. Fluorine has 7 valence electrons, and if we go back to where we were before, chlorine has 7 valence electrons. And you might be able to guess that every element in that column has 7 valence electrons, and you'd be correct. Now if we go back to lithium, lithium has 1 valence electron. Let's add 1 to that. Let's do the one directly above it. We'll do hydrogen. Hydrogen's numbers are 1 and 1. So it has 1 proton on average, no neutrons. And on the first ring we have 1 electron for hydrogen. Correct, put hydrogen there. And so for its Lewis dot structure, it would have an H and a dot. So it makes sense that lithium and hydrogen are both in the same column, and so they would both have the same number of valence electrons. So you could do the Lewis dots pretty easily. Everything in that first column of the periodic table would have 1 dot. Now, believe it or not, the second column would have 2 dots. So that would be beryllium all the way down, and then boron would start 3 dots, carbon 4 dots, and so on. So the most you could have is 8 dots. Now we're kind of ignoring the whole middle of the periodic table. We're just dealing with the tall columns. And the next model that we're going to cover is the quantum mechanical model. Some people call electron configuration. There's all sorts of different things. But what we've looked at is there are many different images that we see, and there are some electrons that orbit spherically shaped. Some of them, you can see a pattern where the electrons do that shape, and they get more and more complex as the electrons move farther and farther away from the nucleus. Now, we call this the S-shaped orbit, and we call this the P-shaped orbit, which P is for primary. It's kind of ironic. The S is for spherical. So those actually have a significance. And if we go to this screen right here, the electron configuration is kind of like giving somebody the address of exactly where you are. You would give your country, your city, your state, your street number, and all that information just to tell somebody where you're at. And we do the same thing for electrons. So this is kind of part of that idea. So if an element is in the S area, that's over there. The P is over here. That's the primary. D has another shape that I didn't show. It's pretty complex. And then we have the F. So it goes in that order. S, P, D, and F. So those are letters that we're going to use with the electron configuration. Now here is kind of a cheating method, but it might work to help you out. You might start with this. The way you use this is you stay on these red arrows. So we would start right up here, and we would go down this arrow. So we go 1s, and then we go to the next one, and we go 2s, and then 2p and 3s, and then 3p and 4s, and so on. Now you might be wondering, how far do we go? What are we doing? How do we know when to stop? Well, there's a couple of things to point out. First of all, we're trying to tell how many electrons. So if we were doing just hydrogen, we would stop at 1 electron. If we were doing chlorine, we would stop at 2 electrons. Okay. The other thing is we need to know how much each letter holds. And I'll put that right down here. The S holds 2, P holds 6, the D holds 10, and the F holds 14. Now if you take a moment and look at your periodic table, you should notice that on the periodic table the S area has 2 columns. And I'll go back to that screen to show you. You can count them out. There are, let's see, there's 1 column here and 2 columns there. So that's why the S goes up to 2. The P has 1, 2, 3, 4, 5, 6 columns. The D, if you count them out, has 10 columns, and the F has 14 columns. So that's why we have the certain numbers for each letter. So going back to here, I'll put our numbers back down. We have 2, 6, 10, and 14. So each time that we use the 1s, we would say a 2. Each time you use the letter P, you would say 6. Each time you would do a D, you would do 10. And each time you use an F, you would use the number 14. So an electron configuration would look something like this. We would go 1s, 2, 2s, 2, 2p, 6, 3s, 2. Okay, so I did 1s, and then I chose a 2. Next I went 2s, and again S always has a 2. Then I went to the P, 2p, and the P holds 6. Then I went down to the 3s, and again the S holds 2. And I stopped because I wanted to go up to 12. So if I add up this, plus this, plus this, plus this, I get 12. And if you look on the periodic table, we would know that we have done the element magnesium. So that would be the technical electron configuration for magnesium. And if we wanted to keep going, we could go to, after 3s, we would go to 3p. And with the P, we would use 6. And then we would go 4s. So essentially, you keep starting off the same way, and you keep going and going and going until you get to the correct number for that element. So we're going to go on to another screen. So earlier we did the Bohr model and the electron, the Lewis dot structure for chlorine. To do the electron configuration, we would do that same diagram. 1s2, 2s2, 2p6, 3s2, 3p. Let's make sure, because we want to only go up to 17. And 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. I know that the P holds 6, but I only need 5 to get up to 17. So that would be the electron configuration for chlorine. And it kind of makes sense that it is in the 5th column of the P block. So if we go back to that screen, we can kind of find out exactly where it is. So back on this screen, chlorine is right down here, and we ended at P5. So it makes sense that this is 1, 2, 3, 4, 5. It's 5 over. And so that would be the electron configuration ending point for chlorine. So we're going to do many more examples in class, and yeah, some of them do get a bit more complicated, but hopefully so far you're understanding. Now in the next one, we're going to do one more section of notes. We're going to do the shortened version of this because there was a shorter one, and we're also going to do orbital notations. Thank you for watching.